something like this, I, j greater than I, 2 over j minus I plus 1, something like that. And this was the expected number of comparisons that randomized quicksort did. And the key to that whole thing was a very, very cute kind of insight to see that this was the probability that the element, the ith smallest element, would be compared to the jth smallest element in an execution of randomized quicksort. And that was the really subtle thing that we spent most of our time on. And if you look in CLR, you'll also see an analysis of randomized quicksort. It may not be exactly the same setup, but it's getting to the same basic kind of conclusion. But their analysis is totally different. They don't have nearly as insightful probabilistic argument. So it's just a lot of heavy-duty summations and manipulations of formula. And you can see how nice it is sometimes when you have just the right cute insight into something. You don't have to do all that grungy arithmetic. So this thing you can solve. What does this look like? How many times does j minus I equal k for some fixed k? I mean, how many times is this? Let's forget the plus 1. How many times does this equal 1, roughly? Yeah, roughly n times. And how many times does it equal 2 is roughly n minus 2. And how many times does it equal 3? Roughly n minus 3, and so on. So we can replace this summation by something like n minus k. And the 2 is still there. N minus k over k. All right, and this is still I equals 1 through n. And this summation then equals 2 over k, the n comes out, minus 2k over k. Oh, what happened to the, yeah, but there's n of those guys, so like that. Okay, so we get whatever this sum is, minus 2n. And what is this sum? Well, this sum is obviously equal to 2n, 1 over k. K equals 1 through n. All right, well, I'll carry along that thing. What's this sum? Nobody recognizes this sum? Is what? Yeah, this is the harmonic series. Okay, this is h of n. So 2n h of n minus 2n. But the harmonic, this is called the harmonic series, and it's about the natural log of n. So 2n natural log of n minus 2n. Okay, and how do you see that this is about the natural log of n? That this summation is about the natural log of n? It's what? Yeah. Right, right. You replace the summation with an integral, and how do you see that the integral of this is about log n? Is because the derivative of log n is about 1 over n. Okay? So, I mean, you do have to bracket it top and bottom, but it all works out. And I think they do that in the book. I mean, in the beginning sections of the book where they remind you of the relevant mathematics, they do talk about the harmonic. So you can look that up in CLR as well. So what we have is the expected number of queries, expected number of comparisons in randomized quicksort looks an awful lot like the worst case number that we came up with for merge sort. All right. And one of the neat things about this analysis, again, is that the randomization is inside the algorithm. You're picking randomly the pivot element. It's not average, or they say the average. The averaging is over the execution of the algorithm, where the randomized elements in there is what you pick as pivot. It's not an average over all possible inputs. Okay, so in fact, it's a stronger kind of argument, because it says no matter how pathological you think your particular input is, if you randomize in the pivot, you can defeat any adversary who's trying to make your algorithm run in n squared time. Okay. So, in fact, it might be a good homework exercise to ask you to try to use this machinery that proved something about every input, but randomizing the choice of the pivot, to use that machinery to prove something that's randomizing or averaging over your choice of inputs when you have, let's say, a fixed rule. You don't randomize on your pivot, but you have a fixed rule for how you're going to pick the pivot.